I'm not even, I'll be honest, I'm not even sure why I record this stuff anymore. I sat through I saw that I got 2 views on one of my videos the other day, and I was laughing because I only check that stuff when I'm uploading new stuff. But when I went to go look at the 2 views, neither one of them made it past the 34-second mark. And like, that's about as much pentatonics as I can take. I'm sure that my voice is probably just as bad. So yeah, that's about all you can take. I can empathize there. I got you. I'm with you on that. So let's do these. This is the number 3 is that roller coaster one. So it has, a roller coaster. Does it have a loop in it too, or just the hill and the jump? Can't remember. Oh, it's just a ski slope. Something like that. That's pretty painfully badly drawn. So we'll go with it. And in my version of the problem, I don't know about your version of the problem, they tell me that the top of the hill is 25 meters. And this is 3 meters. And you have to do a little math to figure out that this angle is 30 degrees. So any questions about any of that stuff? All right, up here, definitely gravitational potential energy. When you're here and you're about to jump, combination of gravitational potential and kinetic. So I don't know what the first question asks, but I can't imagine it's anything that isn't how fast you're going at the jump. Maybe something about what's your maximum speed. But let's see. Oh, it says how far horizontally is there touchdown? So just one question. Good. So this is a projectile problem, but there's no way to do the projectile portion of this problem until we know how fast she gets launched at the bottom. So although I am looking at this as, down the road, we're going to have this vertical and horizontal, I'm going to need that the horizontal velocity, is going to be whatever that v is times the cosine of 30. And the initial vertical velocity is going to be whatever that is times the sine of 30. So we need that velocity, and that's going to be from conservation of energy. So I'm thinking mg times 25 equals 1/2 mv squared plus mg times 3. Any question about that? All right, this gets us our velocity. I don't know what this is. Well, I'm sure there's a number. What's that? 3.8? 20.8? Wow. That's really moving. I guess 25 meters is like a ski jump. That's like 50 miles an hour. Yeah. I don't know that I want to be doing 50 on a set of skis. Yeah. But I mean, it's not like there's a tree in the way or anything, but yeah, no. So I've never snow skied though. I'm sure some of you have. 50? Yeah, I've water skied, but I've never snow skied. So is 50 fast? I mean, would you really? I can't imagine doing 50 miles an hour on a set of skis. I'd be terrified. But all right, let's of course, I've watched the ski jumps on, the Olympics. They're always going down like a slope after the jump. This has level ground. So even if you're going 50, and then you're going a lot faster because the jump is like down slope. Can't imagine. That's just crazy. Delta Y, here's where many of you made a mistake, -3, right? You have to remember that there's a change in the Y position. And I think that wipes out like most of the people who made a mistake. They made a mistake right there. And then our acceleration has to be -9.8 because it's stupid mastering. And we need to figure out how long we're in the air for. So I'm sure you did. I'm sure most people, once they see that mistake, they know what they did, but it's -3 equals 1/2 times -9.8 t squared plus, and then we're going to need to have our 21 sine 30 times t. That has to be positive. You need to figure out how long you're in the air. I don't know what this answer is, but I think most people recognize their mistake, because the number one mistake made here is not realizing that you have a change in height from your launch point to your landing point. So I don't know who asked about number 3. The next part is for you to find the range by just doing this velocity times whatever you get for this time. Is that far enough, or do you need me to go further?
That's good. Thank you.
You're welcome. All right. So number 4. Good progress. Good progress. Number 4. A 1,200 kilogram safe is 2.4 meters above a heavy duty spring. When the rope holding the safe breaks, of course it does, the safe hits the spring and compresses it 44 centimeters. What is the spring constant of the spring? All righty. Is there a cooler one like part B? What's the maximum speed? No. We're going to do a part B on this problem, because if I was going to give you a test next week, and I am, you know I'm going to ask this other question. So let's start with the low-hanging fruit on this one. Why would you be lifting a safe above a spring? Doesn't make any sense to me at all. But we have this condition and then this condition. So I would say this is our initial condition, this is our final condition. Is that good? I have what appears to be all gravitational potential energy here, which I have to take into account the lowest position that I'm going to attain. So that's going to be mg d plus x as the amount of gravitational potential energy there is. At the end of the day, though, all the energy is going to be converted into elastic potential energy. So I'm going to set that equal to 1/2 k x squared. They gave us x and they gave us d. So we are actually looking for k in this problem. So 1,200 is my value for the safe. Yours might be different. And 9.8. And my value for D was 2.4 meters. And my value for X was 0.44 centimeters. That's all I got. We need the value for K though. So can you run that number real quick and get the value for K? Because I'm going to ask an intermediate question. I think you guys know what the intermediate question is going to be. This is probably going to be a pretty big number. Just looking at it. It doesn't compress the spring very far. So I'm expecting this number probably is pretty big. Probably something tens of thousands. What's that? Hundreds of thousands? All right. 35,000. I think you're off by a factor of 10. I think it's 350,000. So we need this for what I want to do next. If I was to ask this question, you guys know the next question I would ask, right? I want to know the maximum velocity. Not because it's much different than the velocity at which it hits the spring, but because it requires you to do something very specific. And I would want that. So now that we've asked this question, understand that next week, I'm going to want to know what its maximum velocity is. And that's going to be when the spring is compressed some different amount that we don't know, but the box will have kinetic energy, it'll have elastic potential energy, and it'll have a little bit of gravitational potential energy if you want to count the lowest place. But we don't have to do that. But we're going to compare that to the gravitational potential energy we had originally. Yeah.
For questions like these where it's like dropped on a spring, can we assume that the max velocity is halfway of the max compression?
You are discovering that it always shows up to be halfway, right? Yeah. The answer to that question is probably, I think if it's dropped on the spring, yes, you'll be able to do that. Yes, sir.
Can you explain real quick why the maximum speed isn't like as soon as it's the spring, why it's further down?
Yeah, because and let's just consider this one space right here where it's compressed the spring a little bit. At this moment, there's mg downwards, right? But the spring has only been compressed a small amount, and the force from the spring is based on how much it's been compressed. So when you first start compressing the spring, you still have an unbalanced force downwards, which is still making the object's speed increase downwards. So as long as there's an unbalanced force downwards, the object's going to continue to accelerate downwards and get faster. So it won't actually reach its maximum speed until mg equals kx. That's when it'll reach its maximum speed.
So even though it's still, when it's touching the spring, it's pushing up a little bit, it's not like the force down is still greater than that.
Right. Yeah. So, I mean, you can eliminate this problem from a question on an exam by just having the spring be only horizontal. But as long as there's an unbalanced force acting on the spring, then the object continues to accelerate in whatever direction that is. This is why, of course, after it passes this point, the unbalanced force upwards is greater than the weight. And that's what's slowing it down.
And does the same go for like it's horizontal?
Now, horizontally, when the box hits that spring, because it doesn't have any force to, let's say the box is moving this way and the spring is over here. When it finally hits the spring, there is no force to the right. We immediately start getting a force to the left that's proportional to how much the spring is compressed. So it starts slowing down immediately because there isn't this force acting on it to the right. It can't be accelerating to the right if there's no net force acting on it. Now, this is not me trying to come up with some way to screw you over, but saying that, I know people in AP. So you can probably imagine that they have as twisted a sense of humor as I, and as twisted a sense of creativity as I. Right? This would produce the same result as what we had, dropping the object on the spring, in that there would be a tension in this direction, and we would not reach our maximum speed until it was balanced by kx. So, when we're trying to look at these problems, I'm not trying to come up with a way to screw you over. I'm just trying to say, in these problems, the maximum speed can't be reached until the net force is zero. That's why where there was nothing on the table, the net force was zero. Until you hit the spring, you were at your maximum speed. But in the spring problems, because we have this unbalanced force, we have to find the point where the net force is zero. Skylar?
I was just wondering if you could put your measurements on the board, since I have different ones for my mastering problem, but I wanted to do it so that it has your numbers so we can check.
These are my numbers.
Your distances.
Oh.
The distances, are they on there?
2.4, and this was 44 centimeters.
Okay,
and the mass
thank you.
1,200 kilograms. So to do this part of the problem, anyways, I want to get through it real quick, but we don't need the answer. I just want to see how it's done. Fudge. Got the blue line staying there. We need this condition to be met, which is going to be 1,200 times 9.8 equals x times 350,000. And from what Kevin's telling me, this ends up being 22 centimeters. Well, I don't know that it's 22 centimeters. You're the one who was saying it was. So it's not 22 centimeters. It's not halfway. All right. So 0.034 represents how much the spring has to be compressed to reach the maximum speed. So now we have to redo all of this. The potential energy has been reset. The potential energy now is mgh, or 1,200 times 9.8 times 2.4 plus 0.34. I make 0.034. Really?
Yeah, that's what
All right, that's fine. I'm okay with that. So 3 centimeters. That's tiny, but okay, that's what it is. Huge spring constant. Yeah. So that's how much potential energy you have. That has to be equal to 1/2 m v squared plus 1/2 k. Even though that's a small compression, you're multiplying by something that's 3.5 times 10 to the 5th. So this is when the maximum speed is achieved. And is it much different than when it first hits the spring? Well, probably not in this case because the spring constant's so big. But if I'm looking to make sure you're doing the problem right, yeah, you can surely bet that there's going to be a point on your exam for understanding where this position is, a point for recognizing you have elastic potential energy because of that, and then a point for setting up your conservation of energy question correctly. So again, if I was asking this question on a test that I think was fit for AP Physics C, I would have that question in there for sure. No, that's the speed. That's the max speed. Now, just so you know, there's like 6 versions of this problem where there's a box already on the spring. And so there's a collision first, and then the problem takes over conservation of energy. So that is incredibly likely on the exam. There's like, over the last couple of years, there's been 6 or 7 like this, where this collision takes place first. So you have a momentum problem, and then the energy problem takes over. So you have to use energy to get the box here and figure out how fast it's going. You have to have the collision, that's momentum, and then energy again to figure out how far it compresses the spring and stuff like that. That's the kind of stuff that you have to expect on the exam. And that's why we got to nail the energy stuff. All right, so next was 6. 6. Truck brakes. Oh, goody. Truck brakes can fail if they get too hot. In some mountainous areas, ramps of loose gravel are constructed to stop runaway trucks. Have you guys ever seen one of these? Truck runoff? Yeah, I lived in Arizona for years, so they're all over the place. Where'd you see them? Yeah, once the grade gets above like 4%, you start seeing these things show up everywhere. I've had to hit the deck having trucks come down the wrong way on some of these narrow roads in the mountains. Truck loses their brakes. There's nothing they can do about it. You better get out of their way. You will always lose against a semi. So, it says it slopes upwards 6 degrees and has a coefficient of friction of 0.37. So let's kind of set that up. 6 degrees isn't very much, but these things are usually really long too. And coefficient of friction, or effective coefficient of friction, of 0.37 for the gravel. And let's see, use working energy to find the length of a ramp that will stop a 15,000 kilogram truck at 35 meters per second. So our truck has all kinetic energy here. And we would like to take all that kinetic energy away. And we want to do so by doing enough work on it so that the truck makes it over here with a kinetic energy equal to 0. So they want us to use the work energy theorem. You could use conservation of energy, but we're going to use the work energy theorem because they suggested it. And I see there's work done by friction and there's going to be work done by gravity. Those are the 2 different forces that will do work. They want us to figure out this length, D. So I'm going to do this as a strict work energy problem, meaning I'm going to do the 3 buckets here, cosine of the angle, and try and make sure that I'm not trying to do a force resolution problem where I'm, resolving the forces. So I'm gonna try and do it this way. And I think we can probably effectively do that because we know most of the stuff that we have to use for this. So when I do that, however, I also want to point out that this sum has got to equal the change in kinetic energy of the system. And this change in kinetic energy is negative. The truck's final velocity is 0. Its initial velocity is whatever, 45 or 38 or whatever, 35. So the work done by gravity, I'm going to do first because it's easier. The force of gravity is downwards, mg. We don't know the distance along the ramp. So, but we do have to deal with the angle between the displacement and gravity, and that's going to be 90 degrees plus 6. So 96 degrees. This will produce a negative answer, but that's okay. All right, next we need to do the work done by friction. Friction is going to be mu mg cosine 6 degrees. I don't really think we have to go through that very much anymore, do we? It's an object on a ramp. I would be happy to if you want to see more about that. Okay. That occurs over distance d, and there's a cosine of 180 degrees between a frictional force and displacement. All right, that's it. So that's the work done by friction. That's the work done by gravity. That has to equal the change in kinetic energy. So we probably all have different numbers. I should stop doing that and just go change them all. But there are some things I can factor out here, but nothing great. So for me, it's 0.37 times 15,000 times 9.8 times a cosine of 6 degrees plus 15,000 times 9.8 times cosine 96 degrees. Oops, what am I doing? You guys should expect more from your teachers. Trying to factor out the D out front of all this. There. So boom. And that has to equal 0 minus 1/2 15,000 times 35 squared. Well, that's just calculator work there. So plug it all in, do your division. This is going to produce a negative sign. This is going to produce a negative sign. But there's a negative sign here, so all the negatives are going to cancel. And you'll get your distance, I don't know, probably hundreds of meters long. If they're trying to use realistic numbers, it's probably 100 at least. Usually this thing is bigger than a football field. But do I need to do more than, I didn't really even want to put the numbers in, but you guys tend to like to see that.
Mr. Shelton.
Yeah.
So with the 96 degrees, that's relative to the work done by friction?
No. It's work done by gravity.
Well, like what is the 96 degrees from?
It's the angle between mg and the direction of the displacement, which is this way. So it's this angle.
Oh, okay. Oh, so you can do negative angles.
96 degrees isn't negative?
Well, circle-wise, that's counterclockwise.
All right, look, you got to realize that pre-calculus has no business in this class.
Okay, so it's just a magnitude.
That's right.
Okay.
Yeah. I'm not trying to be a jerk about it, but pre-calculus has that negative thing going on there because they're trying to teach you something different. It's not going to work for this stuff. All righty. I got it this. All right, I don't want to do any more of this problem. It's just number crunching. It stopped being an interesting problem right here. So after that, I hate the number crunching part. So let's hurry up. We're going to run out of time. So 7.
You skip that.
I can skip 7. I will skip 7 then. So question 9. I don't know who asked about 9, but what's 9? The potential energy for a particle that can move along the x-axis. Yeah, you better be able to do this kind of question. This is on the exam. There's 3 different versions of this kind of problem on the exam. I'm going to talk about at least 2 right now. This is the first, and it comes right from the definition of work. So let me start there. Work is equal to the integral of f dot dx. So quick reminder about that. You may not know this. It's on the equation sheet though, that you take this away. This gives you a incremental amount of work, which means so if you take the derivative of work with respect to position, you get force. The problem is this is not what they're asking about. They gave us potential energy, which is ax squared plus b sine pi x over L. So the second part of this is to understand that when you do work against a gravitational field, the work is negative. So the potential energy stored is negative the amount of work done. So this also equals negative du dx. We talked about each piece of this individually. I had meant to thread it together and never got a chance to, but this is on your equation sheet. You don't have to memorize it, but you do have to realize that they give you an expression for the work in terms of position or an expression for the energy in terms of position. You're going to be taking the derivative to get force. Now, they asked 3 different questions because they asked the force at 3 different positions, but you only have to take the derivative once. So we're going to take the derivative and then make it negative, and that'll give us force. And just so you guys know, the reason why it's negative, I want you to think about this for just a minute. If you're trying to push a ball up, so like say you're trying to roll something uphill, you're going to apply a force. I'm sorry, you're trying to go forwards, but gravity's trying to come backwards. So you get increasing potential energy when you work against the force. So this negative sign is about the direction of the force you're working against, which is why the negative sign is there. So if the potential energy is increasing, it's because the force you're working against is decreasing. It's pointing against you. Anyways, I'm making that sound more complicated than it is. Just take the derivative. So when I do du dx, I'm going to get negative, I have a 2 here, bring it down, 2a times x to the 2 minus 1, so 2ax. And then negative, I have a b here. I'll leave that. The derivative of sine is cosine pi x over L. And then you guys, whether you're in A, B, or B, C, you've learned the chain rule. So I have to take the derivative of pi x over L, which is pi over L. So my whole thing for force is negative 2ax minus b pi over L cosine pi x over L. There. Now, I don't really think you need me to do the rest. It's just plugging in 0, what is it, 0, L over 2 and L. I mean, I will if you want me to go further. I don't know who asked about this problem. Do you want me to plug in the values for x?
I'm good, thank you.
You're welcome. All right. Number 12. We be done. Hey, look at number 10. That one looks familiar. Hey, 11, that one looks familiar. 12, all right. So the spring in the figure has a spring constant of that, is compressed that, then launches that. The horizontal surface is frictionless, but the block's coefficient of kinetic friction on the incline is 0.2. All right. What distance does the block sail through the air? So this is one of those, them being creative kind of questions. So is this AP like exam level problem? Yeah, there's no reason why they couldn't. They've never asked a question like this though, which, that always makes me nervous. So I don't know what your numbers are, doesn't matter. Let's just talk about what you have to do to solve this problem. So I think we all can agree that the spring is going to give the box kinetic energy. And they talk about how much you're going to compress the spring and all that, I think, don't they? So yeah, they give the compression. So you know how much energy is in the system. This is the amount of energy in the system. But the block is going to go up the ramp. And while it does that, although it's going to gain gravitational potential energy, there's also going to be work done by friction. And we're assuming that when we make it up there, the box still has some kinetic energy. So the amount of energy we have at the beginning, 1/2 k x squared, is going to have to be greater than the amount of energy we have at the top of that ramp. So you have to decide how you're going to deal with the work done by friction. I'm writing it like this because, as I talked about in a couple of the classes, and I'm not sure if I talked about it in yours, how do you deal with the work done by friction? You can subtract it from the amount of energy you started with. That'll ensure that there's less energy at the end. You can say that over here, you're going to add the work done by friction as if that's something that happened during the course of the problem. Or you can say that there's a change in the internal energy and put it on that side. But you need to do something to turn that inequality into an equality so you can figure out the exact amount different that you have. So I know the way I tend to look at it, but I know I need you to recognize that wherever you're going to do the part about the work done by friction, it has to lower the initial energy of the system. So I'm just going to put it on this side because if I do it that way, I can just make this an equal sign by just scribbling on it. So at this point, there's not a whole lot of physics left. We've kind of explained the physics. This is just going to be MGH because we have that. We do need to come up with an expression for the work done by friction. We know that the frictional force is going to be mu mg cosine theta. That part we know because the frictional force is going to act this way. And they give us the angle of the ramp as 45 degrees, so we know the angle of the ramp. What we don't have is the length of the ramp. We have this height, but we don't have the length of the ramp. So we have to get the length of the ramp, which is going to be, for me, this height was 2 meters. So the length of the ramp is 2 divided by sine 45. Any question about where I came up with that stuff? So this is how much friction there is. I'll have to multiply by 2 over sine 45. And then I have to multiply by the cosine of 180 degrees. Careful, I am intentionally trying to see if I can get you to make a mistake. Are you paying attention? Because there's a problem. I did something wrong. I'm trying to see if I have people paying attention. Yes, sir?
The cosine of 180 would make it the original like state of the problem, you're adding it on already.
Thank you. That's what I need you guys to pay attention to. When we do work, remember, we're talking about energy. And we already had a discussion indicating this work was taking away the energy from the system. If I follow through with this cosine, I'm going to create a negative number here, which is going to have the result of making these numbers bigger, not smaller. We need to be aware that the whole point of discussing whether the work is positive or negative is to try and come to grips with where the energy went. We're calculating the energy that was taken away by friction. We're not doing this as a strict work problem. We don't need this here. We already took that into account when we placed the work on this side and added it. It's one of those things. I don't have a good way of being consistent here because there is no good, consistent way to deal with that. This is how much energy we're talking about. You need to decide how it gets placed over here. You need to decide that. Because conservation of energy, all the energies are supposed to be positive. You're just laying out where those energies were, either before, after, or during. So once we've done that, I think you guys can finish up the problem on your own. Now it's just plugging in numbers and figuring out how fast it's going. After that, it's a projectile problem. I don't feel like we really need to review a projectile problem, but I will if you are desperate to see it. All right. Then I'm going to end here unless there's another question on the homework.
Mr. Shelton,
Yes, Sander.
what would we set the angle to if not 180? Just
Well, let's understand what that angle's about. It's supposed to be about how much of that force is in the direction of motion. Now, we purposely set this up in such a way that we have the force in the direction of motion. It's opposing the motion, which is what's taking the energy away, but it's along the direction of motion, so 0 degrees.
okay, that's what I thought. I just wanted to confirm. Thank you.
No worries. All right, guys, that's it for today. The bell rings in what, 3 minutes? So there's not time for me to do the demo. I am going to be giving you some momentum questions to do on collisions. They're probably going to be due middle of next week. I won't make it super long, but it's going to be enough for us to prepare for the test. All right? All right, guys at home, do you have any questions for me? All right, then feel free to log out whenever you wish. I give you these 2 minutes back. You can have these 2 minutes to do with as you choose.
Have a good weekend, Mr. Shelton.
You do the same, Xander.